Okay, welcome to another exciting class, Significant Fellow. I remain Mr. Simplicity. Today we are going to continue with special limits. In the last class, we were able to look at the first case of special limits. Here we talk about limit as x tends to infinity, that 1 over x is equals to 0. So today we want to look at the other three. Remember I said we'll be talking about 4. So we want to look at the other three special limits. I'm going to put them on the board now, explain the three of them, then we'll take examples, series of examples where we can apply them. So the first one we are looking at today, which is the number 2 for special limit, is limit as x tends to 0 sine x over x is equals to 1. So what that simply means is that anytime we see x tending to 0 in a limit and we have the trigonometric function of sine, we can apply this rule to it. Come again. Anytime limit tends to 0 and we are dealing with the trigonometric function of sine, we can apply this limit to it. It actually means that if I'm solving a problem, limit as x tends to 0, and I come across a sine function, something of this nature, maybe carrying ax raised to power n, I can make it look like this guy, and then it will be simplified. How do I do that? This is what I need to perform the operation. I'll use it to multiply, I use it to divide. So if I use it to multiply, I'm going to have ax raised to power n. If I use it to divide, I'm going to have ax raised to power n. So all of this will be 1. Is that okay? So that's what the first special limit, the second special limit is about. And this third one is similar to it. The third one is when limit tends to 0 and we are considering the trigonometric function of tan. So this is what the second limit says. It says limit as x tends to 0 tan x over x is 1. If you compare with sine, they are exactly the same thing, which means anytime limit tends to 0 and you have the function tan, you just need to make it look like this, just as I did for the sine, and then you will have 1. So we'll look at an example on it as well. Then the fourth one says so limit as x tends to 0 cos x is 1. That's what this one says. Then if you observe, you discover that the first two are similar, but the last one has a slight difference, but they all tend to 0 and they are all 1. So with that, you easily remember them. Okay, so now let's go into solving some examples. Okay, so if we look at this problem, it has to do with sine and limit tends to 0. So that means it's a special limit. So what I need to do, remember that the rule says if we have sine x over x as limit tends to 0, everything is 1. But now I'm having sine 10x. Then what I need is that I need to introduce over 10x. And I cannot just introduce over 10x like that. I need to bring something equivalent that can take it back to normal sine 10x. So if I put 10x here to multiply, they can cancel out and it still remains sine 10x. So this is the logic. Anytime you have the sign of a function in a limit, a special limit, just take whatever the sign is carrying to multiply it and to divide it. Then you have the opportunity of making it a special limit. So this becomes limit as x tends to 0. This will become 10x sine 10x over 10x. So I introduce 10x to multiply, I introduce 10x to divide. You get it? Introduce 10x to multiply and introduce 10x to divide. That's for the numerator. We go to the denominator now, we are going to do the same thing. So the denominator is carrying 3x. So this will be 3x sine 3x over 3x. So this is what we need. So we can deal with the others individually. In that case, x can cancel out. When x cancel out, we'll be able to have limits as x tends to 0 10 sine 10x over 10x over 3 sine 3x over 3x. As soon as you arrive here, you can see we can record the special limits now. That limits as x tends to 0, sine x over x is 1, making all of these to become 1 and all of these become 1 in the next step. So when I come here now, I'm going to have 10 times 1 over 3 times 1. So this is now 10 over 3. That's the final answer for that question.